In this chapter, we will cover definite integrals and areas. Definite integrals are antiderivatives set over a range of values. This means that x will take any values between a and b. The notation is pretty similar to the indefinite integral case. We use this sign, but in addition, we need to specify the ranges where x lies, from a to b. This means that we will integrate from x equals a to x equals b. The computation of definite integrals follow a similar procedure as in the indefinite integral case. But there are two differences. First, definite integrals do not have a constant. And second, once we obtain the integration, we replace the values of x with first the upper bound, which is x equals b, and we will subtract it by the value of the function at x equals a. Notice that the final result will be a number, which is the second difference with respect to indefinite integrals. To understand this concept, let's solve these two examples. Let's compute the integral of these two terms. The integration of the first term is the following. Here 2 is the constant times the variable part, which is x, and the integral of x is x squared, because here the exponent is 1, and when we integrate we add one more unit to the exponent, divided by 2. This is because when we integrate, we divide the whole expression by the new exponent of the variable, plus, for the case of the second term, 6 is the constant times the integral of x squared is x to the third, because we are adding one unit to the exponent, and we divide the whole term by the value of the new exponent, which is 3. So far, this is pretty similar to the case of the indefinite integral. However, here we need to write the boundaries, and we normally use a bar, and we say that the integral goes from x equals 1, which is the value of the lower bound, to x equals 2, which is the value of the upper bound. Before we start with this computation, let's simplify a little bit. Here 2 divided by 2 is 1, so we have here x squared, plus 6 divided by 3 is 2. And again we write from x equals 1 2x equals 2. Notice the second difference with respect to indefinite integrals. Here we do not write plus c. Now that we found the integration, we can replace with the values of x equals 2 and x equals 1. Let's replace with x equals 2. This is going to be 2 squared plus 2 times 2 to the third. This is when x is equals to 2. When x is equals to 1, we have 1 squared plus 2 times 1 to the third. This is when x is equals to 1. We subtract the value that we obtain using the upper bound minus the value that we obtain using the lower bound. 2 squared is 4. 2 to the third is 8 times 2 is 16. 16 plus 4 is 20. 1 to the third is 1 times 2 is 2 plus 1 is 3. 20 minus 3 is equals to 17. This is the result of this definite integral. Let's continue with this example. Again, we have two terms. The integral of this first term will be 4, which is the constant part, times the integral of x to the third is x to the fourth divided by 4 minus the integral of 1 over x is a special case. This is natural log of x. And this will be integrated from x equals to 1 to x equals to 4. Before we proceed with the integration, we can make simplifications. 4 divided by 4 is 1, so we have x to the fourth minus natural log of x. That goes from 1 to 4. Now let's replace the value of x equals 4, which is the upper bound. This will be 4 to the 4 minus natural log of 4. Minus, here we have x equals 1. This is 1 to the fourth minus natural log of 1. This is when x is equals to 1. 4 to the fourth is 256 minus natural log of 4 minus 1 to the fourth is 1. Natural log of 1 is 0. Then this is 256 minus 1 is 255 minus natural log of 4. And this is the solution of this definite integral.